Sample problem number 2, we are looking at normal force. In this case, we're going to determine the normal force in the following situations. First, we're going to take a look at what the normal force is going to be when we simply have a 20 kilogram mass sitting on a level table. As a reminder, the normal force is the reaction force from a surface, and that surface will respond to whatever mass or mass plus other forces are applied to it. So in part A, we have a single 20 kilogram mass sitting on a table. Part B, we have the 20 kilogram mass sitting on the level table, but we have an additional force of 3 newtons acting down. So what we want to focus on is what this additional 30 newtons does to the situation with respect to the normal force. In part C, it's the same 20 kilogram mass, but in this case, we have a 30 newton upward force acting on the mass. So what's different about part B and part C is what role the normal force has to play in both cases. So here's our given setup. So in part A, we just have a 20 kilogram mass. In part B, we have the 20 kilogram mass, but we have a downward force, and that's what the F subscript D stands for, of 30 newtons down. And in part C, we have the same 20 kilogram mass, but with the upward force of 30 newtons up. The relevant formula in this case is the weight formula. The force of gravity is equal to mg. So let's take a look at the first free body diagram in part A. So what we have is we have our 20 kilogram mass sitting on the table, and it is not falling or rising, which means that it's just sitting on the table, which implies an acceleration of 0 meters per second squared. Because it's not falling at this point, it's not moving. Now, for this to be possible, we have to have the forces in balance. So when we look at the free body diagram, you can see that the magnitude of this normal force has to be the same as the magnitude of the weight, but obviously in opposite directions. So I use this expression quite a bit. Objects are not floating or sinking. So if the object isn't floating or sinking, that implies that there is no acceleration. If there's no acceleration, that means that the net force is 0 newtons. So let's take a look at our formula. The net force formula is equal to Fn plus Fg. These are the only 2 forces that are acting on the object at this point. But since it is not accelerating, the net force also has to equal 0. Dropping the vector notation, we know that the normal force is acting up and the force of gravity is acting down. And the formula for the force of gravity is Fg equals mg. And let's just clean that notation up a little bit there. Next step is to bring this negative mg term to the other side using the opposite of subtraction, which is of course addition, following the rules of SAMDEB. And then we're left with the magnitude of the normal is equal to the weight, which is pretty much expected at this point. Substituting in, we get 20 times 9.8 or 196 newtons. Therefore, the normal force is 196 newtons up, except it needs to be 196.0 newtons up if we wish to have the appropriate number of sig figs. Now let's take a look at the situation for part B. In part B, we are still at rest. It's still sitting on the table, which means that the acceleration is 0 meters per second squared. If the acceleration is 0 meters per second squared, that must mean that the net force must also be 0. So the big idea here is that the sum of all the forces acting up must be equal to the sum of all the forces acting down with respect to their magnitude. So I often refer to this as team up and team down. Now in this case, the downward forces work together to add more pressure onto the table. So we've got the Fg and that Fd. As a result, the table has to push back even harder to prevent this from falling down. It does this by slightly flexing and compressing at the molecular level the atoms a little closer together. And when you compress them a little closer together, they naturally produce additional repulsion force because of the electrostatic repulsion between the valence electrons on the atoms themselves. Basically, if you think of the molecules as being attached by little springs that don't want to be compressed, the more you try to compress it, the harder it resists. And that's why the normal force continually compensates. And that is, of course, up to a limit, because eventually you'll simply cause the table to fail. You'll break it. Now, the vector equation in this case is Fnet is equal to Fn plus Fg plus Fd. There are 3 vectors acting in the vertical. They all must add up to 0. So the net force is equal to 0. the normal force is positive, the weight is negative, and remember Fg is equal to mg, and this downward force is also negative. This implies that Fn now is just a magnitude because the direction has already been extracted out front. Mg is just a magnitude. That's why little g is always just 9.8, and the negative implies down. And Fd is negative already here. So the value we put in for Fd will just be the magnitude because we've already brought out the direction. This means you have to be extremely careful that when you substitute in for Fd, you don't substitute in a negative number again, because you've already made it negative. If you put negative here, a negative times a negative would make a positive. So you can't do that. That would undo the direction. So of course, the next step is we have to bring both these terms to the other side. The opposite of subtraction is addition. So when we bring them to the other side, they become positive. So we get Fd plus mg equals Fn, or Fn is equal to Fd plus mg. And remember, the Fd, just a magnitude because we already made it negative up here. And this gives us a value of 226 newtons. Now, if we compare that to the answer in part A, the normal force was 196.0 newtons. In this case, the normal force is now 226.0 newtons, which is 30 newtons greater, making sense because the normal force now has to resist with much greater force. Finally, part C. In part C, the balance of power, as it were, has changed a bit. Now we have two forces acting up, the normal force and the upward force. They're working together. And since they are working together, combined, they need to match the force generated by the weight. Again, the acceleration is 0 meters per second squared. And since it is not, and that's because it's not floating or sinking, therefore we know that the net force must be equal to 0. So when we have the upward force plus the normal force plus the force of gravity in vector notation here, when we drop the vector notation, the upward force is positive, the normal is positive, and the weight is negative. Again, we're isolating for the normal force, which means we need to bring the negative mg term and the positive upward force term to the left-hand side. And by doing so, their signs will flip because the opposite of addition, of course, is subtraction, and the opposite of subtraction is addition. So we get mg minus f subscript u is equal to Fn. Turning the equation around, we've got mg minus the upward force. Substituting in, we get 20 times 9.8 minus 30, and that gives us 166 newtons. Now, the normal force in this case, as you can see, is actually lower. And that is because it is being assisted by that additional upward force.